Are you ready to journey into the enigmatic realm of black holes? These mysterious cosmic phenomena, often depicted as the universe's all-consuming monsters, certainly possess a charm that's hard to resist. What exactly are black holes? How do they betray their presence? And how have scientists managed to recreate their unique properties? We'll delve into these intriguing questions and many more in today's video. Stay with us till the very end as we unveil how black holes, once thought to be pure destroyers, could play a critical role in the cosmic cycle of creation and dissolution. Are you ready for a journey into the unknown? Let's dive in. Considered to be cosmic devourers, black holes are perceived as menacing entities in the cosmos. Yet, they cannot be measured through conventional physical means, at least not entirely. They disclose their existence in two ways. Their immense mass distorts the gravitational forces around them, and they emit slight but discernible radiation. This radiation carries a special significance, and in today's discussion, we'll delve into its unique nature and the lab-based efforts to replicate it. Astronomers have detected enormous black superholes at the center of most galaxies. Over millions and billions of years, these black holes consume entire star systems. However, in today's video, we'll be concentrating on what comes out of these cosmic giants. It was long assumed that nothing could escape a black hole. Once something enters a black hole, it doesn't come out, and no one can ascertain what the black hole has consumed, as no information escapes. Physicist Stephen Hawking demonstrated that these assumptions were only partially accurate. A mysterious luminescence appears at the edge of black holes, now pursued by scientists, the Hawking radiation. There is a point of no return around a black hole, beyond which any matter is inevitably sucked in and disintegrated until only information remains. This information, regarded as the ultimate source of creation in scientific circles, must still exist in some form within the black hole. Researchers currently don't know whether this information might find its way out of the black hole in some other world, time, or dimension. Loving the video or learning something new? Smash that like button and don't forget to subscribe for more awesome content you won't want to miss. Stephen Hawking discovered a phenomenon at the edge of these cosmic giants that indicates information does escape black holes, albeit subtly, in our universe. At the event horizon, an unusual split occurs in quantum fluctuations. In physics, quantum or vacuum fluctuations are essentially nothingness. Particles and antiparticles constantly appear in the vacuum or seemingly empty space, briefly exist, neutralize each other, then vanish. At the event horizon, a fascinating division occurs. One particle is sucked into the black hole and the other shoots off into space. These escaping particles emit a tiny amount of radiation, dubbed after its discoverer, Hawking, who proposed this revolutionary discovery back in 1975. Despite its theoretical perfection, the actual existence of this radiation couldn't be confirmed. Black holes are too distant and their radiation too minimal. Yet, an intriguing phenomenon occurs when these two particles that raises significant questions. According to quantum mechanics, particles and antiparticles remain forever entangled. Thus, the particle that enters the black hole maintains a constant quantum level informational connection with its counterpart that shoots off into space as Hawking radiation. This entanglement implies that the freely flying particle carries the same information as the particle inside the black hole. Theoretically, by examining or decoding the information of a particle from the event horizon, we could potentially discern what transpires within a black hole. This concept is undoubtedly intriguing, but we are currently far from being capable of extracting or interpreting the full information content of tiny particles. As previously mentioned, we have yet to even measure Hawking radiation, or at least we had not been able to. This is because researchers have now devised methods to create black holes in the lab. There's a degree of apprehension regarding these experiments in the scientific community due to the uncertainty surrounding the potential impact the smallest black holes could have on the fabric of space-time. For safety, the experiments are conducted with incredibly simplified models. Scientists in Amsterdam discovered a method to safely demonstrate the event horizon and basic functions of a black hole in a controlled environment. For the miniature event horizon, they constructed a chain of basic atoms capable of perfectly imitating the barrier effect. By adjusting the interconnections between the atoms, they could recreate cosmic phenomena up to the point where the enigmatic radiation suddenly appeared. Initially, the scientists induced electrons to leap from one atomic site to another in this one-dimensional atom chain. This leap was analogous to the barrier crossing of particles at the event horizon. By manipulating the connections between the atoms, the leaps of the particles could be made either easier or more difficult. This artificial event horizon permitted a series of tests and led to intriguing results. In a specific state, thermal radiation suddenly emerged on the atomic chain. Simply put, this means that there was the presence of heat or oscillation. However, this radiation only occurred when the atomic chain extended beyond the artificial event horizon. If the chain concluded at the barrier, the glow ceased. Simplified, one could say that the radiation only occurs when the particle that crosses the event horizon remains entangled with the other one that shoots into the cosmos. Consequently, the interaction of these two particles is responsible for the creation of Hawking radiation. According to Dutch researchers, this validates Hawking's theory. But the results of these riveting tests not only confirm Hawking's correctness and the fact that something does emanate from black holes, but they also raise intriguing questions. If these particles are information carriers and possess, in essence, a direct line into the interior of a black hole, we need to question what these information do in the material cosmos, our known space-time. You likely have a few questions that you're eager to share with us in the comments. But before that, we'll examine another aspect of Hawking radiation which could have significant implications in the cosmos. Black holes diminish. The tests also revealed that black holes do not all radiate equally. Black holes, due to their immense mass, alter the curvature of space-time. Like planets or stars, they exist within the cosmic web of space-time, creating colossal distortions. The greater the space-time curvature caused by a black hole, the less radiation is emitted from the event horizon. Smaller, lighter black holes bend space-time less and emit more radiation, and hence more information. In physics, this radiation of information essentially means that due to Hawking radiation, a black hole gradually, yet steadily, loses mass. Therefore, black holes are not eternal and indestructible phenomena, but entities that lose mass over billions of years and will ultimately disappear. Now let's revisit the end of time scenario. As we discussed at the start of the video, some scientists believe that at the universe's end, a colossal black hole could have consumed all matter. But now that we understand that a black hole continually expels information, albeit subtly, the perception of the universe's ultimate end shifts slightly. If even a minuscule amount of information escapes into space, matter can form from it. Of course, we remain unsure of how a supermassive mega black hole, potentially the last one in the cosmos, would behave physically. It's plausible that a certain size and information density within the hole, Hawking radiation could cease. It's conceivable that black holes serve, at least partially, as recycling mechanisms rather than exclusively destructive entities. This notion provides a fresh perspective on the grand question of the origin of creation, the beginnings of matter, and the evolution of our cosmos. Some cosmological models suggest that our universe didn't arise from a singular starting point and won't end at a specific endpoint. Instead, it might be a self-generating, self-sustaining system. The role of information exchange at the edge of black holes in this process. remains to be seen. Undoubtedly, future research will yield improved methods to simulate black holes more intricately and safely. Simultaneously, our technological capability to directly study black holes in the cosmos will also likely enhance, and maybe we will ultimately uncover the profound secret of what occurs within these giants. Until then, let us know your comments in the comment section below. And if you enjoyed this video, be sure to give it a thumbs up and subscribe to our channel for more captivating content about science and the universe. Thanks for watching.